Assalamualaikum warahmatullahi wabarakatuh. Today I want to present my project. My title of my project is Topology Optimization Upper Control Arm of Double Wishbone using Aspire software. So my name is ARIF DANIAL bin FAIZAL EFFENDY from Technology Automotive. So my supervisor is Encik Ahmad Zulusni bin Encik Mamat. A double wishbone suspension is an independent suspension design. This suspension using two wishbone-shaped arms to locate the wheels. So two wishbone shape divided into two parts, which are upper control arm and the lower control arm. So each wishbone has two chassis, mounting point, and one knuckle joint. So next we go to the problem statement. So the problem is unnecessary or load on the suspension system. And then by this unnecessary load will consume the high fuel consumption of the car. After that, consequently, mass reduction of vehicle component is offered as a means to reduce the identified issue. So therefore, the purpose of this study is to reduce the mass of vehicle by removing the low stress region in the suspension system. And then for the objective, the main aim of this thesis is to reduce the weight of the rear upper control arm without affect the performance of the control arm. So the first objective is to reverse engineering the actual part of the upper control arm by using the CAD software. Second is to reduce the mass of the control arm by topology optimization using a CAE software. So last objective is to conduct a comparison study in terms of von Mises stress and displacement. And then we jump to the scope of research. For my scope of research is rear upper control arm of double wishbone suspension type. So using CATIA to design the actual part with the mass accuracy not less than 95%. So the topology optimization by Altair inspired software. So other scope of research is performance study of the base model and optimized part. Focuses on displacement, von Mises stress, and the mass. So the target mass reduction in between 30% to 50% of rear upper control arm. So the lastly is the analysis will base on the linear static analysis. And then we go to the summary of my literature review. So the first journal I found is a design of analysis of lower control arm of suspension system. So in this paper, they calculate the force acting on the lower control arm of a four-wheeler with critical loading condition. So in this paper, McPherson suspension type has been chosen. After that, the static analysis performed to determine the location of maximum deflection and stress. So the part design carried out by using the Autodesk Inventor software. The dimensions are physically measured to get the design. So the part design is meshing by using the HyperWorks software. In this meshing, a 3D meshing contains hexa and penta element. So after that, they analyze the meshing part to find the low stress region. So in this paper, they manually redesign the part and remove the low stress region. During the static analysis, the displacement was found to be 3.425 mm and the von Mises stress acting on the lower control arm was 176.3 megapascal. And then we jump to the next journal, which is a topology optimization of lower control arm for light motor vehicles. According to this paper, they choose the control arm of McPherson suspension type. In this paper, they use a technology such as a coordinate measuring machine to measure all the dimensions of lower control arm, and then they generate the measurement and import into CATIA because CATIA has a special tool of generative surface design to construct a typical surface, which is then they converted into a solid model. After that, ANSYS software is used to meshing the CAD model. A solid tetrahedron element is used to meshing the CAD model. In this paper, they apply a static structural analysis to determine the force, stresses, strain, and displacements. After that, topology optimization is done by ANSYS software to find a removal path from the low stress region. In this paper, they manually redesign the control arm to find the optimized model. After that, they import the optimized part into ANSYS for further static structural analysis. In this paper, they achieve a percentage of cost saving in material for optimized lower control arm over existing is 16.57% from the base model. And then for the last journal I found is a new design optimization of lightweight front lower control arm. So this paper proposed the design optimization of aluminum cast from the front lower control arm to investigate. So the first step is CATIA software was utilized to design the lower control arm, but this paper, the difference between the other journal is they use the concept design. So the initial conceptual design of a front lower control arm with a solid design, which is the actual part the actual part is a stamping part, and then they turn the design concept of the front lower control arm. After that, HyperWorks software was used to analyze the structural strength and optimize the part of the weight. The original weight almost 3.4 kg, so they target a new design was a 20% weight reduction from the existing part. After they run the optimization, the based on the final design of concept of a front lower control arm is a 2.55 kg, which is about 25% of weight reduction that they achieve. For the base model, I have choose Subaru Impreza GD 2.0 WRX STI, which is the 10th generation of Subaru. So this is a sedan car which have a 4 doors. This car use independent suspension system for both axle of the car. So the front suspension using the McPherson suspension type and a double wishbone suspension type for the rear tire. So for this study, I focuses the rear suspension because it have a bulky upper control arm that have been chosen for this study. So the mass of upper control arm is 3.25 kg that can be optimized. So the wheelbase, the specification of the car, which is the wheelbase of the car is 2520 millimeters. The length of the car is 4420 millimeters and the width of the car is 1740 millimeters. So the curb weight is 1425 kilograms that can help us to find the reaction on each tire of the car. So the material is a cast iron that has been used for the rear upper control arm that has been produced from Subaru. Next, we go to the methodology part, which is more interesting. And for the methodology, the first step I'm doing is reverse engineering the actual part. by measure all the dimension of rear upper control arm by using the vernier caliper, the micrometer, radius gauge and the feeler gauge to get the exact dimension. After that, I convert the measurement into CATIA. So by using the CATIA, I start design the rear upper control arm with a solid design based on the measurement before. So from the picture, I have done the actual part in the CATIA. So after done the CAD design, I make a mesh comparison between the actual part and the CAD part. So the result I get is the mass of the CAD part is 3.21 kilogram while the actual part is 3.25 kilogram, which is 1.02% difference between the actual part. So after that, the linear static analysis is done by Altair inspired software to find in terms of von Mises stress and displacement of the best model. So the next step is topology optimization of the best model. So topology optimization is done by using the Altair inspired software. So the first thing I made, I import the CAD file from the CATIA into the Altair inspired by using the STL file from the CATIA. So the next step is to define the parameter by applying the material and define the part which fix is not to be removed, such as a chassis mounting and the knuckle joint, and applying the force on the ball joint and support at the chassis mounting hole. After that, optimization the actual part and minimize the mess. So the last step after I run the optimization process is to make the organic shape become smooth by using the polynerps features in Altair Inspire. So we jump to the last part, which is a pre-result part. For the first picture, this is a CAD model that I import into Altair Inspire. So the first step, I set up the actual part by make a partition at all the hole. After that, support and loads apply on the part before I run the optimization process. So the second picture, which is the organic shape. The organic shape has been generated after I run the optimization. And then we go to the last picture. After the organic shape has been generated, I use the features in the Altair Inspire, which is a polynerps features, to apply on the organic shape to make the organic shape become smooth design. That's all from my pre-result for my project. That's all from me. Thank you for lending me your ears.